Okay, let's look at some just projectile intro. We look at horizontal motion and vertical motion are different, since in the vertical direction we have gravity acting on us. So we have acceleration is g. And we know that gravity acts downward. So if we're looking at the equations, it depends on kind of what the reference frame that we're setting up is of what we're adding and subtracting on things. But you guys know that distance is equal to velocity times time. And with horizontally, it goes in it. We do not have gravity acting on it. So we're going to just look at it as if it's going at a constant velocity, because it is. There's no other forces. But what happens if there's air resistance? If you were launching a ball, really there's not a whole lot of air resistance unless it's going very fast, very large, or a lot less dense than the environment it's being launched in. So this is a case for any normal kind of situation that you'll be doing in a classroom. We look at a constant velocity in the x direction, unless otherwise discussed about air resistance. So you can see that it goes, if you look at just kind of how far it goes in the x direction every second, these little marks are showing the every second, and you can see how it goes the same distance in the x every second. Okay. Now, the velocity, if it's 5 meters per second to begin with, we could put a little 0 on here saying an initial original velocity in the x direction, but it's the same throughout. So that's why, there we go. The initial velocity in the x direction is the same as the velocity when it hits the ground, right before it hits the ground. So constant acceleration, in that case, we have an acceleration, so we need to add the acceleration component to it. And we need to also put that this is the y direction. So the initial velocity is in the y direction. And the initial velocity in the y direction. Everything is in the y. Now, when you look at time, it does not have a direction to it. So it's the bridge. Any of the variables on the constant motion side, if it's in the air, it's the time it's in the air is the same for horizontal and vertical, and that's how we connect the two together. So let's look at, as we go down, it's going a little bit faster, and the next second's going a little bit faster, and the next set's going even a little bit faster than that. Well, how much does it accelerate? Well, it's about 10 meters per second every second. So in 1 second, the velocity in the y direction, let's see what it is going originally. 0 meters per second for this one. Then it will be going 10 meters per second. Then it will be going 20 meters per second. And then in the end, it's going to be going 30 meters per second in the y direction. Write that down a little bit lower. Yeah. So it keeps going faster and faster and faster. So really, let's take a look at what happens if we did not launch it horizontally, but instead we launched it up and to the right. Well, in that case, we have a horizontal initial velocity, and we also have a vertical initial velocity. So in that case, our vertical initial velocity is not 0. So what's going to dictate how long it's in the air? The height at which the object falls or goes up, and initial velocity in the y direction will affect the time in the air. That's key. Okay? The time in the air is only dependent on the initial velocity in the y direction and kind of the height. So in this case, the height's going all the way down to the bottom. This one here, time is going to be, so the height that it's falling, whatever you're looking at, the time that's in the air, the time that, if you're only looking at it at a certain point, then you're looking at the height that has fallen to that point. Now, notice we don't have an initial velocity in the y direction for the top one here for a horizontal launch. So that one is a little easier to work with. We'll go ahead and do that in the next episode with horizontal launches, and then we'll look at angle launches.